Okay, this is chapter 5.3, proving triangle congruence by SAS. All right, SAS, that is side, angle, side. So essential question says, what can you conclude about two angles when you know that the two pairs of corresponding sides and the corresponding included angle are congruent? Okay, kind of a complex question there until you look at the exercise as an example. Okay, so what you will learn in this chapter is use the side angle side congruence theorem, SAS, and solve real life problems. So let's take a look at SAS. Okay, so theorem 5.5 is the side angle side congruence theorem. And it says if two sides and the included angle of one triangle are congruent to two sides and the included angle of a second triangle, then the two triangles are congruent. So what are they talking about here? Let me get my highlighter. Let me make it a little bit thinner. So it says if side AB, which is right here. Hello, I made it thinner, did I not? Side AB is right here. And notice the one arc. If AB is congruent to DE, so there's the one arc there, and angle A is congruent to angle D, and AC, which is this side right here, is congruent to DF. Notice we have a yellow and a blue line segment meeting at a vertex D, and we have a blue line and a yellow line segment meeting at the vertex A, and all three pieces are congruent, then we can say the triangles are congruent. The lengths of these two sides plus this angle measure will force the remaining angles and sides to be congruent to the other triangle. And the proof is on page 246. And let's take a look. So after this statement right here, this theorem, if you have a pair of congruent sides with an included angle, meaning the two sides that are congruent form that angle, to a corresponding triangle that's the same, then the triangles are congruent. So now you should be able to do the problems 3, 4, 6, 9, 10, and 12 just by this theorem. Okay, so example 1 says, using the side angle side congruence theorem, write a proof. So we're given BC is congruent to DA. Okay, there's our first given. BC is congruent to DA. So the statement's going to be BC is congruent to DA. And there's this little S over here signifying that that is one side congruent to another side. So the congruence, actually, let me leave my highlighter here, just make it smaller. The congruence is saying BC is congruent to AD are these congruent markers right there. So whenever you have a given, always label your diagram. So BC is congruent to AD. The next thing we're being told is that BC is parallel to AD. Okay. So that is this right here and this right here. Okay, that's hard to see with the red, but let's do this instead. So this congruent marker and this congruent marker here, or not congruent, but the parallel logos on these two sides say that BC is parallel to AD, and that is a given. So the diagram is labeled with the two givens. We're trying to prove triangle ABC is congruent to triangle CDA. So if you will, this is triangle 1 and this is triangle 2. We're trying to prove they are congruent. So we start with the statement, BC is congruent to DA, and that's a given. And then what we're going to say is 2, BC is parallel to AD. Well, that's also given. All right, so then what do we do with that information? Well, we can now say angle BCA is congruent to angle DAC. So let me mark that. BCA is this angle and DAC is this one. So what I want you to realize when you're doing this is content we've already done in this course is going to keep coming back. This right here is a transversal. AD is parallel to BC and AC is a transversal. Therefore, these two angles are alternate interior angles. So the alternate interior angle theorem is the reason those two triangles are congruent. And notice there's an A over here. So we have S, we have A. So we have a side and we have an angle. Now all we need is one included side to prove these two triangles are congruent. Well, what forms angle CAD? Well, it's the transversal and it's AD. Well, we know AD is congruent to BC, so AC is shared. Well, when something is shared, it's equal to itself. So AC, segment AC in triangle 1 is congruent to segment CA in triangle 2. And that is because of the reflexive property of congruence. Something's, reflexive property, something's equal to itself. And there's our third side. So we have a side, we have an angle, we have a side. We are done. We can now state what we're trying to prove, which is triangle ABC is congruent to triangle CBA. And the reason is SAS. Okay, and it's that easy. So let me move these markers out of the way. And you'll be able to see it if I label this now. This side is congruent to itself. So I have this side and this side with this angle. Notice it's included. It's in between the two marked sides. This side's marked congruent, and the blue markers here make this congruent to itself. And this angle is formed by those two sides. So we have side, angle, side, and going this way, AD, angle A, or I can't call it angle A, angle DAC, and AC. So we have SAS, SAS. Okay, so that's how you construct a proof. Okay, so I highlighted this diagram before I started this portion of the video. It says example 2, using side angle, side, and properties of shapes. In the diagram, QS is this line right here. QS is going through the center of the circle. So QS is called a diameter. It goes right through the center. Okay, so it is called a chord. We haven't gotten to circles yet, but it's called a chord. But when it goes through the center, it's a diameter. It's the longest possible chord in a circle. And RP is also a diameter. And so therefore, since all radiuses of a circle, all radii are congruent, then that's how we're going to solve this problem. We have vertical angles. So we have angle PMQ, which is right here, and angle SMR. They are congruent. So I can say angle PMQ is congruent to angle. And if I start with P and I go to M, it's got to be RMS. So I know those two angles are congruent because they're vertical. And all points on a circle are the same distance from the center, which means the segment MS is congruent to the segment MQ. So I can say that. MR is congruent to MP. They're all congruent. So I can say MR, segment MR, is congruent to MP, is congruent to QM, is congruent to, actually, I don't want to go that direction. I want to go MQ, start in the center. So let's say MQ, and that's congruent to MS. Okay, so MR is congruent to MP, is congruent to MQ, is congruent to MS. So in looking at one triangle, MQ and MP are two sides where the angle in the middle is included. MS is congruent to MR, which is congruent to MP and MQ. Since they're all congruent and the vertical angles are congruent, then these two triangles are congruent by side angle side. Okay, I'm not going to write that, but that's what well, why not? We should. So we could now at this point, we can say triangle, and it doesn't matter how you name it. If I start at M and go to P and then Q, triangle MPQ is congruent to triangle MRS by SAS. Okay, and that's basically it right there. So at this point, with those types of diagrams and what we know about SAS now, problem numbers 19, 20, and 22 should be able to be done. Okay, solving real life problems. Example 3, solving a real life problem. You are making a canvas sign to hang on the triangular portion of the barn wall shown in the picture. So we want to put a canvas sign on this wall. You think you can use 2 identical triangular sheets of canvas. Okay, you know that RP is perpendicular to QS. So that is labeled in the diagram. So I'm use green, it'll be standing out better. So there's the angle diagram. There's the right angle diagram telling us RP is perpendicular to QS. And PQ is congruent to PS. So PQ is right here. There's a congruent marker. PS is over here. That is a congruent marker. Okay, so it says to use the SAS congruence theorem to show that these 2 triangles are congruent. Well, we already know that they're perpendicular, forming a 90-degree angle. So if that's 90 degrees, this is 90 degrees because QS is a straight line. So now we have an angle in each triangle. We have a side in each triangle. So there's our side, and this is our angle. All we need now is another side, and it is right here, RP. So now I can say RP is congruent to PR. And that's because of the reflexive property. Okay, so this is congruent to itself. So I have a side, I have an angle, I have a side, I have a side, I have an angle, I have a side. So now I can say this. I can say triangle PQR is congruent to triangle PSR by SAS. Okay, pretty straightforward. And that is problem number 3, or example 3. So now you should be able to do problem number 27. Okay, so that brings us to the end of a very short exercise. Quit complaining. It's over. All right, so now do these problems. And thanks for watching. Have a good day.